Hello, my name is Richard Smith, and for those who know you, I'm always trying to learn something new and demystify something for myself. So I've worked with teams, managed teams that are working in AI, machine learning, robotics. So I'm trying to dig into it and see, can I understand it? Do I understand it? What are they talking about? So that's my attempt today to talk about that. What I'm going to use as an example, and this is for image classification and machine learning. So I found this great tutorial online, which I'm showing on the screen here, and by AI-Specials, but very few subscribers, but this is a really good two-part introduction. So I basically went and followed that. What it uses is Jupyter Notebook to do your coding in and programming in, and we need two, one for training and one for inference, as it's called. So again, trying to work out what do they mean by all these things? What are my people talking about? What are the teams talking about? So that's what I'm going to do in this video. So the first thing is, what are we actually trying to do here? So let me just move over to my File Explorer. And what you'll see here is we have robotics, where is it? Image classification, scene detection. So we have these images, and they're images of various things, and it's an image set that you can get off Craggle, as it's called. Just a site for getting these. And it's various things, buildings, images of the sea. And what you're trying to do is train a model. So this machine learning, train a model, neural networks, all that wow stuff, to recognize as you use a training set, and then you have another set that is used to test your model, and then you have a set that you use because the test set, and you know the answer, but then these you don't know the answer. These are the predictions, and so we have to look at these and say use the model and see if it accurately recognizes it. So is this a building? Is it something to do with the sea? Is it something to do with mountains? So those just happen to be this image set, and what the clarification, what the different types are, and different classes as I call them. And this set has been 25,000 images that someone has painstakingly gone to and said, yes, that is a mountain. Yes, that is the sea. Yes, and they've annotated it. So they've taken the image and they've put data related to it to say, this is what it is. I've confirmed, I'm a human, I've confirmed this is correct. Then the machine learning thing has to learn from this so that you don't have to tell it anymore. You've given it enough data, it should recognize it. That's the whole point of this. So going back to the notebook. So again, this is just a programming environment, so it's not too mysterious, but it does save you a lot of effort of trying to set up your own machine and do it locally. But anyway, so what I'm going to do is I'm going to run through two things. Sorry. So what I'm going to do, I'm going to run through two things. This is the training code, and I'll just give you quick highlights of it, which is interesting. And you've seen all the data we talked about. So again, you need to have various things in here. Some exciting stuff is Torch. So this is the PyTorch library, and so this is a machine learning system. You don't need to know a lot about it, but this is the heart of it, right? Because you have to give it the data, it comes up with a model, and then you can use the model. So this is also very interesting. So it's checking to see if your computer has a graphics card that can be used to do the processing on. So CUDA cores, it's NVIDIA thing. So if you don't have a graphics card that supports that, it just uses your CPU, and it is about 3 or 4 times faster if you have the graphics card that supports these CUDAs, just so for my testing. You then have things where you're taking in the data and the images in this case, and all the images are 150 by 150. You're going to resize it, you're going to mess with it, get it ready to be fed to a system. There are, where's all our stuff? Where's our training set? Where's our test set? Now this is the heart of it. This is the convolution neural network, or convoluted, whichever. It all sounds similar to me. So what it does, and this is from, I did not invent this, but I did type every single letter of this in and test it, and I made mistakes and I fixed it. But what it is doing, it takes data and it says it has a shape, right? And the shape of the data is basically an array. It's 256 colors, it's RG, no sorry, 2 for batch size. We're going to set the batch size 256. We're going to set that it is images. It's RGB is what we're looking at, red, green, blue, and here is the size of the data, right? The height and width of the images. And then you do this convolution, as it says. Now in the person who's created the original video, it's interesting because he explains this a bit more. But this is the basic. You take some data and you convolute it, probably messing up that term, and you make it into something else. So this now data becomes this shape. So the shape of the data, the dimensions, that's what I'm seeing it as. You then do a few things to clean it up, but then you're now reducing the size of it, which will help you process faster. You then do another convolution, so X channels in, X channels out, don't fully understand it. You can do as many of these as you want, and this is where the strategy of a machine learning person will know stuff that I don't know. But you're doing these convolutions, you're doing these steps to the data to process it, get it ready for feeding it into the engine. And you get, at the end of it all, you get an output. And you go, this is going to give you the output of taking a set of data and doing all those transforms on it, doing all those convolutions, and doing it. So then we go down to the heart of this thing here. So there's things called epochs. Epochs is different. Epochs on you, as they would say in Monty Python. And this is a number of iterations you're going to run this whole thing through. It's 2 is too small, but takes a long time, or 10 takes a long time. And then you're saying, okay, how many of these things how many images do I have to count, to train, to test? And we're doing some printouts. So we have 14,000 images and in the training set, and we have 3,000 in the test set. So then they have this loop. So we're going to go through the loops to a number of epochs we have. I keep on saying that wrong. Epochs. So we're trying to look at training accuracy and get to a point where the training accuracy is high enough to say this model is working well. But anyway, so we go through all of the data. We do various different things. We get the output of it. We determine the loss. We're counting the loss to see, we're trying to find a point where the training data is accurate enough. And I've just put in some printing here to time me, so I'm not sitting around looking at the computer wondering what the hell is it doing. This is for evaluation, and at the end of it all we say save the best model. So we say when the accuracy, if the accuracy, whatever the highest accuracy we get, so we run an epoch, goes through everything, churns it, and comes up with an answer going, oh, it was this accurate and we lose this much of fidelity, or whatever the loss thing means. And then you can run it again and run it again and run it again. But you want to take the one, whatever the best result you had there of all the runs you do, you say that is my model. And that's what this is doing. And then it just says it's saved it. So it saves the model, and we call it this thing, best checkpoint. So a checkpoint appears to be an epoch in this case. And you can see down below here when I ran this the last time, you can see some information here. So we start on it. So this is the important line. So at this line we said the loss was this, the training accuracy was 0.5, and the test accuracy was this. Now that is horrible. It should be above 90.9. 1 is perfect. You can see the second run it went to 0.67, and the test accuracy, so the training accuracy was this and the test accuracy was this, so it's increasing that's just in the second run. Now if you do only 2 runs, if you only do 2 runs, it will be a crap model, so the model will not work well, and it will give you wrong answers. It'll look at the image of a sea and call it a mountain, and I've checked it myself. So I was only doing 2 runs, got a model, used it, and realized it was just crap. In this case we're into the training mode. We do that, and then we do evaluation mode, and we take different data, those different set of data. We have the 3,000, and we come up with a model. So that's the first part of it. The second part of it is using the model. So again, this is another Jupyter notebook, and you see a lot of this is the same, right? But anyway, so again we have training path of data, and now we have the prediction path. So the prediction path is, so these are just the pictures we're going to use to that we don't know anything about, and we're going to say feed it into this beast and see what it thinks they are. And again, where is it? So again, you're going through this. Let's go back down to this loop here, prediction. So here is actually the prediction thing. So we take in the image, we transform it into a tensor, because that's what the engine needs to recognize as not an image. And a tensor is just a different form of the same data. And here is the actual loop we're doing. So we're going through the images in the path, which is the prediction path, and we're going to make a prediction on it, and we get an answer. And then when you actually do that, it does work. It actually looks at the path, looks at all the images, uses the model. So where did we load the model? Let's go back to where I loaded the model, because I didn't. Yeah, okay, so here is where I loaded the model. So I have the check. I said, okay, where is the best model? So you remember this name, best model, from the last time. It's been loaded into Torch effectively, and then it calls the convolution again, and it loads the state, and then it does an evaluation. I don't know what this means, but you're basically doing the same operations, but you're now using the model you have. So you can take that model and plug it in anywhere. So just like here, you can call it up, do it, and it actually works. 10 iterations, got it very accurate. 2 iterations, it was actually, you saw the number is probably 60% accurate. So what do you need to know? You need to know that there is a bunch of data preparation. Going back to this stuff here, where is it here? You got this classification step you have to do. You have the amount of information. If you have 20 images, this isn't going to work because it needs more churning. So you have to have thousands of images or hundreds of thousands of images in many cases. But you can also get this training set is available off Kaggle, which is, I'd never heard of, but that's where a lot of free training set data is. But anyway, so you get the data, you need a lot of it. You have the steps that you're going to run through, this convolutions. You're going to what am I going to do with this? I mean, because I can have it just as input and output, but I need to do some stuff, manipulate and mess with it, and that helps the engine apparently. But again, I think there'll be a lot of experimentation in this section, or experience, or saying that for certain things, certain different convolutions and different steps will give you a better answer. Machine learning isn't this magical thing, it just happens. There's a lot of preparation for it, and it can give you the wrong answer as well if you don't actually do enough training, pretty much like us humans. So that's it. That's just a quick run through what I discovered on this. So kudos to any team that's working on this, because there's 1,000 nuances. There's the parameters and the various different things. This is just scratching the surface, but at least I feel I see some of the tasks involved, some of the potential, not pitfalls, but actually just you could just go in many different directions with this and get lost in details. But what is the best model? What's a good enough model? What is your application? It's going to matter. If it's life threatening, it probably needs to be perfect. If it's something about picking candy out of a range of candy, how good does it need to be? I mean, okay, so that's it. It's just a quick run through image classification in this case, and how it used convolution networks. Okay, so thanks for listening, and this was just an investigation, trying to understand what's going on in the world of machine learning, and in this small tiny part of it. Okay, thanks, bye.